Come on in, everyone. Feel free to ask any questions if you have them. Waiting for everybody to come in. No questions? All right, well, looks like we got 9 of you folks, and it's already 24 after, so I guess it's probably best if I go ahead and proceed. Again, I'll ask, does anyone have any questions before we move on? Anything about homeworks or anything like that? Oh, another person came in. So no questions? Well, last time we started into chapter 18, we essentially got the most important stuff done. Really, what I care about is your ability to apply the Maxwell distribution, uh, at least in the ways I showed you and the ways that I hinted at. Your ability to use the average kinetic energy is equal to 1/2 m v squared bar, which equals 3/2 kT. That's again the translational kinetic energy, so you should be able to use that. And then the ideal gas law, of course, that's continuing from chapter 17, so you should be able to use that. I've got a couple of problems I planned on working for you today regarding that as well, but also other quote unquote equations of state. And your book does a really nice discussion of P versus V diagrams and P versus T diagrams, and discusses things like boiling point, triple point, critical temperature, critical pressure. All those terms are things you should know as, educated scientists and engineers. So definitely read over that. And there are actually some questions I could put on your test from that. So make sure you're up to speed on that. All I really wanted to do beyond that was I wanted to make sure you were aware of basically 2 other equations of state other than the ideal gas law. So I did tell you that we are not skipping. In fact, you're supposed to be responsible for real gases and change of phase. So that's something you guys should be able to do. I'm trying to find out. I was hearing some noise. Looks like it's gone now. Looks like everybody took care of it. Okay. Also, vapor pressure and humidity. I said that's perfectly reasonable for you to do those calculations on homeworks, practice tests, and stuff like that, but I'm not going to actually test you on it. So vapor pressure and humidity is something you should read so you learn it, but I'm not going to test you on it. Same thing with evaporation, vapor pressure, boiling, partial pressure and humidity. Temperature decrease of boiling water is another one, but I'm going to jump down to van der Waals equations of state, and we are skipping mean free path and diffusion. So hopefully that's enough. So let me just reiterate exactly real quickly what, actually, hold on, I got to do something with my stuff here. Let's see if I can copy this page. Nope, not that one button. Copy page. And I think I can put it right here. And it'll work properly. See if I can paste page right here. Paste page right here. That'll work. Okay, so what I wanted to do is introduce you to van der Waals equation, explain to you what the motivation of it was, and just roughly give you an idea of what the Clausius version looks like, as well as van der Waals equation looks like. So to do that, let me start off by, again, we had a couple people sign in, so if anybody has any questions while I'm in the process of transitioning to my iPad, feel free to ask any questions you might have. I'm going to go ahead and start sharing my screen. So it's loading, and you should be able to see it pretty soon. We already know the 2 versions of the ideal gas law. Again, I use lowercase p, so PV equals nRT, where R is equal to 8.314 joules per mole Kelvin. So if you're using like pascals for pressure or newtons per square meter for pressure, you can go ahead and use that version of R. And that's the one we usually use in physics. There's also this other version of the ideal gas law, which is PV equals N KT, where K is equal to 1.3807 times 10 to the negative 23rd. And that's joules per Kelvin. And last time I mentioned that, in fact, Avogadro's number times the Boltzmann constant is the R that we use. So that's where they actually came from. Now, the problem with the ideal gas law is it doesn't work if the pressures are too high. And it also doesn't work if you're close to liquefaction. In other words, when you get to such low pressures and low volumes that the intermolecular or the molecular forces of attraction between the individual molecules, as well as the actual sizes of the molecules, come into play, then you start to have problems. You have problems in that the molecular forces are making the pressure a little less severe because they're trying to keep all the molecules near each other. And it's actually making the volume a little bit less too, because some of that volume is being occupied by the actual molecules themselves. And that's what van der Waal tried to actually deal with. And first off, van der Waal did it, and he lived from 1837 to 1923. And around the 1870s, he actually reached a conclusion using kinetic theory and statistical mechanics and stuff of that sort. And one first order correction, which isn't his, by the way, but probably he went through it, was this one. And it's basically, let's take into account the volume of the individual atoms or molecules that you're using. So instead of PV, you're going to say P times V minus N times B, where N is the number of moles present in the sample, and B is the volume of a mole of the molecules. And again, this is where we're using the word molecules, but we understand in some cases it actually might refer to individual atoms. So this is volume of moles per molecules per mole. Okay. And then the other side, of course, would just be the regular nRT. So that's one version. This is called the Clausius version. I think that's what it's called. Let me look that up real quick, just make sure. Yeah, that's well, that's a version of the Clausius equation of state. Okay, if you want to divide through by n, though, it can get a little bit more pretty. And when you do that, you end up getting P. Whoa. You end up getting P times parentheses V over N minus B is equal to RT. So that's a little bit cleaner version, but still essentially the same equation. So you can see that that's one way you can deal with the finite size of the molecules. You don't have as much volume to work with. In fact, some of the volume is going to be taken up by the atoms and molecules, and they actually increase a little bit with in size with temperature, but not very much. So it's really not that big of a deal as far as the temperature thing. It really is just ultimately the volume. In general, though, you would use experimental data to actually decide what B was. You can do a theoretical calculation of it, but generally we're not quite at that level. Or I mean, we can take pokes at it and get rough estimates, but generally speaking, you could always just do an experiment because it's going to be different for every gas. And if you more or less know the gases that you'll be dealing with, just do all those gases. Or if you're in industry and you work with some specific gas, and that gas might be somewhat secret, like proprietary or something, then in-house they would derive that B experimentally for that particular gas. But if you want to go further and start to take into account the fact that the forces act and stuff like that, then what we've discovered is van der Waal realized that the pressure would actually be inversely related to the density of the molecule. So reduction in pressure would be proportional to the density of the molecules in the layer. And ultimately, that version or those versions give us something like this. So what they're going to do is they'll say the pressure is equal to RT. So we're sort of starting off with the second version of Clausius. So RT over V over N minus B, but then they want to reduce it by some scalar A that again can be experimentally determined. And what they're going to do is say that that is inversely proportional to the density, only they're going to use the density in volume, or excuse me, in number of moles per unit volume, and that's going to be squared. So that's what you can do. And if you want to simplify that a little bit further, you can ultimately just say P plus A over V over the number of moles squared, parentheses around it, times V over N minus B, parentheses around it, is equal to RT. And those are the van der Waals equations. So if I give you one of those equations and ask you to calculate something, I've got to give you A and B unless I'm specifically asking you for A and B. So these are called actually, let me write it in blue. These are called, actually, no, I did the other one in red, might as well. So van, that's a lowercase van. And lowercase der, and then uppercase W, AALS. And this is equation of state as well. So you just write EOS. And that applies to both versions. So that's the van der Waals equation of state. And for instance, for CO2, your book gives you this data. For carbon dioxide, experimental data suggests A experimental is about 0.36 newtons meter to the fourth over moles squared. You should be able to convince yourself that that's the appropriate unit, and definitely that's a worthwhile exercise. And B is equal to 4 and this is experimental as well, is equal to 4.3 times 10 to the negative fifth meters cubed per mole. Okay. So that gives a slightly different sort of scenario. And when your book was talking about the curves that came with PV equals nRT, you basically just got a series of hyperbolas when you did pressure versus volume. Basically, high pressure corresponded to low volume, and low volume and high volume corresponded to low pressure. So it was just a curve that went down and to the left, almost like exponential decay, but it wasn't exponential decay. It's what they call a hyperbola, because it really is PV equals nRT. Basically says P is equal to some constant over V. So that's really what the functions are. But as you read the sections on real gases and change of phase, what you saw is that curve being smooth like that wasn't the case. In fact, what happened was the curve would come up, and then it would, as a bare minimum, level off for a split second at the critical point, and then bolt back up. And then if you actually had a change of phase, it would go up and go level for a period of time and then up. And then this one actually gives more along the lines of something that goes up, goes down and up, and then back up again. So I think that's enough really to give you an idea what to use. So van der Waals equation of state is to be used, and I'll again repeat, not to be tested on, so I'm going to write these sections down. That all looks good. That looks good. That looks good. So section 18 dash 4 dash 4 and 18 dash 5 and 18.7 and 18.8. So just to remind you, this is diffusion. This is mean free path. (18.5) is temperature decrease of boiling. And the 18.44 is actually partial pressure and humidity. Whoa, Nelly. Okay, so hopefully that's explanatory. So now that I've done that, let's go ahead and solve some problems, because that's really what's most important in a calculus-based physics course. Is yes, you need to learn the concepts. So a lot of those have to come on your own by reading the questions, taking pokes at the questions, and then checking out the answers. Also doing the concept homeworks and stuff like that. So let's move on to our first example. And I've already written it out. It says calculate the density of oxygen at standard temperature and pressure, assuming it behaves as an ideal gas. So this is an ideal gas law problem. And oxygen implies O2 basically, which means the molecular weight of O2 is 32.0 grams per mole. So that's something that might come in handy. Standard temperature and pressure. Standard temperature and pressure means the temperature is equal to 0.0 degrees Celsius and the pressure is equal to 1.00 atmosphere, which equals 1.01 times 10 to the 5th Pascal, which by the way is the same thing as 1.01 times 10 to the 5th newtons per square meter. Okay. So what we have is the ideal gas law says PV equals nRT. Of course, N is equal to the mass divided by the molecular weight. Okay, so you can put that in and get PV is equal to the mass over the molecular weight of O2 times R times T. And now you can see, oh, density, which is what we want to know. Density is mass over volume, so I can reconfigure this and write P over RT is equal to M over V, and I can put MO2 on top. So that looks like it. So what we're going to do is we'll say the density of O2 STP should be equal to the mass over the volume, which we discovered was the pressure times the molecular weight of O2 divided by the ideal gas constant times T. So the pressure is going to be 1.01 times 10 to the 5th Pascal. The molecular weight is going to be 32.0 grams, technically per mole. And the R is going to be 8.314 joules per mole Kelvin. Okay. Now you see the Pascal is a Newton per square meter and the joule is a Newton meter. So can we leave that grams up there as grams per mole? or do we have to make that into kilograms? Anybody know? Yeah, you actually have to convert it to kilograms or the units don't work out, as you'll see in a second. So I will take and say 1,000 grams is equal to 1 kilogram. And then what you'll see is this gram cancels out with that gram. This Kelvin cancels out with that Kelvin. This joule right here is a Newton meter, which is a kilogram meter squared per second squared. And this Pascal right here is a Newton per meter squared. So, also, I can also do this mole right here, cancels out with this mole right here. And you see that the Newton in the Newton meter below cancels out with a Newton above. So I'm going to use a green one to show this. That Newton's going to cancel out with that Newton. And then this meter squared down here in the bottom is actually on the numerator. So when you put it to the top, it's going to become in the denominator. And then I got a meter squared in the bottom already. But you can see that the kilogram that's actually necessary is going to have to come in there as well. So that looks like it's all working out. You might want to try this on your own just to make sure that the units all work out, but I've sort of given you a blueprint to that. So 1.01 e to the fifth times 32 divided by 1,000. That's my numerator, which I get 3223 or 3232, sorry. Now, if I just look at the units that I've already canceled out, it looks to me like I've got, oh, that Newton canceled out. Sorry about that. I got kilograms over meter squared in the numerator. And then in the denominator, I do 8.314 times 273.15. And that gives me 2271.0. Actually, I should say 71.0. And those units turn out to be the meter. Yes, just the meter on the top. And that's it. So ultimately, you see that because we did convert that to kilograms, we ultimately get a density of kilograms per cubic meter, which is exactly what we want. So I'm going to say this is 1.42. Carrying one extra sig fig. And that is kilograms per cubic meter. Of course, we're talking about a gas here, so you do expect it to be this low, and the gas is just oxygen gas. Any questions on that? No questions? All right, let me turn on my, I keep forgetting to turn this back on. I want to turn on my chat so I can see that in case anybody's answering questions or asking questions via chat. All right, so that's one problem. Let's shoot for another. Actually, this wasn't what I wanted to do. Let's do this one. Let's do copy page. I think I want to copy it right here. Let's see. Paste page. Yeah, that's good. So here's another example. 4.00 cubic meters of a gas is initially at standard temperature and pressure, is placed in a pressure of 3.00 atmosphere, and the temperature rises to 40 degrees Celsius. What is its final volume? So this is, in principle, another ideal gas equation. But there's a nicer way to use it that comes in handy. and sort of circumvents the PV equals nRT. PV equals nRT is the ideal gas law. But if you have a fixed number of molecules, so it's a closed container where molecules or atoms can't leave the container, then you can go ahead and say PV over T is equal to N times R, and all this part is a constant. So what we can do is say P1 V1 over T1 equals P2 V2 over T2. And later, when we introduce adiabatic conditions, we'll find that there's a relationship that you can use in addition to this one, so you can solve for even more variables. So what we have here is we have the initial pressure, standard temperature and pressure is going to be, and by the way, other than having to use Kelvin, you can use any pressure you want here, and you don't have to look up a different R. That's another advantage of using this way. So the pressure is going to be 1.00 atmosphere initially. The volume is 4.00 cubic meters. That also can be any unit you want, as long as you use the same unit on the other side. And the temperature, of course, was 273.15 Kelvin, which you always have to use Kelvin. Now, the other pressure, they said, is going to be 3 atmospheres. And the volume is what we're looking for. But the temperature is going to be, instead of 0 degrees Celsius, it's now 40 degrees Celsius. So that's 310 or 313.15 Kelvin. So now we see that V2 should be equal to, what I'm going to do is take the 1.0, I'm going to multiply that by 4, and I'm going to divide that by 273.15, and that gives me 0.01464. Oh, I missed a 0. 1464, carrying clearly at least one extra sig fig. That actually gives me units of atmospheres, cubic meters per Kelvin, and that's just this first part that was on the left side of the equals. Now I'm going to multiply that by 313.15 Kelvin over 3.00 atmospheres. So I'm going to multiply this by 313.15, and then I'm going to divide that by 3, and that gives me 1.529, and the only unit left is cubic meters, because you can see this atmosphere cancels out with that atmosphere, and this Kelvin cancels out with that Kelvin. Any questions on that? So you could have done it the alternative way. You could have actually used PV equals nRT. Then you could say, use that to solve for N. So I'll say alternative. PV equals nRT allows you, since it was 4 cubic meters, we can use that. The pressure was 1 atmosphere, so I can say 1.01 times 10 to the 5th Pascal times 4.00 cubic meters is equal to N times 8.314 joules per mole Kelvin, and then that times the temperature, which is 273.15 Kelvin. That allows us to determine what N is. So I'm just going to take the 8.314 and divide it by multiply it by 273.15. And now I'm going to divide that by 1.01 times 10 to the 5th. and I'm going to divide it by 4. So you could put parentheses around it and then divide by 1.01 times 10 to the 5th times 4, close parentheses. This gives me 0.005621 moles. And now for part 2, we've got, so for the new situation, we've got the temperature is 313, and the pressure is 3 atmospheres. So I'm going to write it as PV equals nRT, and I'll put a T2 on all this. So this one's going to give me 3.03 times 10 to the 5th Pascal. That's what 3 atmospheres is, times the volume V2, which is what they want to know. That's equal to 0.005621 moles times 8.314, and that's joules per mole Kelvin. And then that's times 313.15 Kelvin. So from that, you get V2 is equal to, I'm going to take that 0.005621 or 5621. I'm going to multiply it by 8.314. I'm going to multiply that by 313.15. And now I'm going to divide by 3.03 times 10 to the 5th Pascal. And lo and behold, I get, whoa, that's different. Did I use something funny? Let me check my math again. Hold on. So we did have the temperature, make sure I use the right temperature, the standard temperature and pressure. So that was 1 atmosphere and 273 and 4 square meters. Yeah, let me double check my math on my, did anybody double check my moles? Because right now I'm getting 4.830. Well, dang it. Times 10 to the negative 5th. So it's clear something went wrong. I'm not sure what did, but let me see. I want to check my calculation for n first. So I'm going to say 1.01 10 to the 5th times 4 cubic meters. Now I'm going to divide that by parenthesis 8.314 times 273.15, close parenthesis. There you go. So yes, I must have typed in something differently. Did anybody get the same answer I did for the number of moles? I didn't see anybody. No, good. Shanda did not. All right, so let me change this real quick. What I'm going to do is I'll just draw a red line through it and say, what I really got was this time 177.9 moles. I don't necessarily trust that, so I'm going to do the calculation again. 1.01 e to the 5th times 4. Now I'm going to divide that by parenthesis 8.314 times 273.15, close parenthesis. I get the same answer again. So I think that's right. Anybody else get that same answer for n? All right, now I'm going to do this. I'm going to erase this like I never got an answer. Be fine because I've shown the correction here. So what I'm going to do is do this 177.9. I'm going to multiply that by 8.314 and then multiply that by 313.15. So that's my n times r times t. Now I'm going to divide that by 3 atmospheres, which is 3.03 e to the 5th. And that gives me the answer I got before, which is 1.529. Whoa. So you see, either way will work. And of course, we put that in cubic meters, and using the particular R that we did also gives us cubic meters. So that checks. Anybody have any questions on that? So you can see the PV over T is a much easier way of doing things. So I want you to keep that in mind. As long as you're justified, meaning the other variables that you're not using are not changing. So in this case, for instance, the number of moles was the only thing that wasn't changing. So it was perfectly acceptable to use PV over T equals PV over T. But in some cases, the temperature might change, in which case you get in which case you get P1V1 equals P2V2. T can change, or T can't change in that case. Okay, but you can also use P1 over T1 is equal to P2 over T2. And that's when V and N are constants. And of course, you could also use V1 over T1 equals V2 over T2. And that's when P and N equals constants. Okay, so those are the versions that you can use. I think that's all of them that you can use for the ideal gas law without actually using N and R. So that comes in handy a lot of times. Notice all of them definitely require you to have N equals a constant. Otherwise, you'd have something like PV over NT equals PV over NT. That works as well. You could do that. But anyways, that's it. Any questions on that? All right, so that's the one we just did. This brings me to another ideal gas equation, or another ideal gas problem. The ideal gas problem says calculate the number of molecules per cubic meter for an ideal gas at standard temperature and pressure. So you might not necessarily think of this, but this is a perfect time to use the other version of the ideal gas law. Remember, PV is equal to nRT, but also PV is equal to the number of particles. That's what the capital N stands for. Oops, let me just erase that. That looks like crap. PV equals N, KT works as well. So we're actually asking for the number of molecules per cubic meter, which is really N over V. So PV equals N KT gives us P over KT is equal to N over V, which equals number of molecules per cubic meter. So we can say N over V is equal to P over KT. And of course, the P for standard temperature and pressure is 1.01 times 10 to the 5th Pascal. The K is 1.3807 times 10 to the negative 23rd joules per Kelvin, and the temperature is 273.15 Kelvin. You can see, of course, this Kelvin is going to cancel out with that Kelvin, and this Pascal is a Newton per square meter, and this joule is a Newton meter. So basically, you end up getting the newtons canceling out, and I just get per cubic meter, which is exactly what we expect for a number per cubic meter. So if I do this math, I'm going to say 1.01 times e to the fifth, and I'm going to divide that by 1.3807 e to the negative 23rd times, still in the parentheses, of course, 273.15 Kelvin. And this gives me 2.67. And the next digit is a 8 followed by a 0. So I'm just going to call that 2.678 times 10 to the 25th molecules per cubic meter. So about 100 times Avogadro's number. Not quite 100 times, but you can see it's obviously 10 to the 23rd versus 10 to the 25th here. So that's about 100 times bigger. Anybody have any questions on that? I see Richard try to come in. Now, you still could have done it with the other way. You just would have had to calculate the number of moles and then multiplied that by Avogadro's number. So an alternate solution might be N, I'll do N per unit volume like that. Obviously, from the ideal gas law, you can see, let me erase this real quick. From the ideal gas law, PV equals nRT. You can see that N over V is actually equal to P over RT. So N over V, which equals number of moles per cubic meter, okay, that is equal to 1.01 times 10 to the fifth Pascal divided by 8.314 joules per mole Kelvin times 273.15 Kelvin, which equals that gives me 44.47, carrying one extra sig fig, moles. Notice I'm saying moles, not molecules, per cubic meter. And then N over V is equal to N times Avogadro's number over V, which equals 44.47 moles per cubic meter times 6.022 times 10 to the 23rd. And this time it's going to be molecules per mole. And you can see that the moles actually cancels out with the moles and gives me molecules per cubic meter. So I'm going to multiply this by 6.022 e to the 23, and lo and behold, I get 2.678. It actually deviates. I had 6780. This has 6782 times 10 to the 25th. And that's molecules per cubic meter, which matches again. Any questions on that? All right, so next what we got to do is get you a little bit used to dealing with groups. For instance, the Boltzmann distribution gives you basically a distribution of velocities for a given velocity range from v to v plus dv, for instance, has f of v times dv molecules with that speed. So what we're asked here is we have a group of 25 particles. Let's count them, make sure they add up right. So 2 plus 8 is 10, plus 4 is 14, plus 2 is 16, plus 6 is 22, plus 1 is 23, plus 2 is 25. So that does look right. And their speeds are 2 particles have speed of 11 meters per second, 8 have a speed of 17 meters per second, 4, 19, 2 has 25, 6 has 29, 1 has 34, and 2 has 39. And it wants to know A, the average speed, B, the root mean square speed, and C, what is the most probable speed. And I like this because it really lays out exactly what these terms mean in ways that you can actually calculate it easily. So here's our solution. I'm going to say A, the mean. So we're going to say V bar is actually equal to, I'm going to take the 2 particles and multiply that by 11.0 meters per second. I'm going to take the 8 particles and multiply that by 17.0 meters per second. I'm going to take the 4, multiply it by 19. So this is just basically like, if I actually had it without the number of particles, it would be 11 plus 11 plus 17 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 until I got through all 8 of them. And I keep doing that. But because I've got them evaluated like this with numbers, I'm trying to tabulate it. That's the word I was going for. Tabulated like this, and I can just multiply instead of adding. So that makes it a little bit easier. 2 have 25, so I'll say 2 times 25.0. Notice I've stopped writing the units. Okay. So I'll just put a little dash in here just to remind us that technically there are units. 6 times 29. And 1 times 34, I'm just going to play 34.0. And then 2 times 39. That. And then notice I've added them all up. Now I'm just going to divide them by the total number, which is 25. And what I get is 2 times 11 plus 8 times 17 plus 4 times 19 plus 2 times 25 plus 6 times 29 plus 34 plus 2 times 39. That equals 570. And that's 570.0 meters per second divided by 25, which I think you can see is basically 22.8. So if we divide that by 25, we get 22.8 exactly. So that is the average velocity. Now, what is the root mean square velocity? Well, what we have to do is take the average of the squares now. So for part B, I'm going to say VRMS is equal to the square root of V squared bar, like that. So I'm just going to put a big fraction bar there. I'm going to say 2 times 11 squared. I'm leaving off all the units here just to save a lot of paper, a lot of space. 17 squared plus 4 times 19 squared plus 2 times 25 squared. And I could put them inside or outside of parentheses. It doesn't really matter. Plus 6 times 29 squared plus 34 squared plus 2 times 39 squared. All that divided by, again, 25. And then all of that is raised to the 1/2 power because we're going to take square root. As you can see, when we squared the 11, 17, and so on and so forth, that became meters squared per second squared. So it had the wrong versions. I just saw Richard's note. Everybody else can see the screen, right? For sure, you might have to log out and log back in if that's the issue. But I'm going to go ahead. Yeah, I thought everybody would have told me, so just making sure. All right, thank you. So now what I'm going to do is I'm going to go ahead and compute that, and I'm going to get the values and then put them under the square root so y'all can check your work intermediately. So I'm going to say 2 times 11 squared plus 8 times, this time it's 17 squared. Now your calculator knows that when you put a square, it only applies that to the thing immediately to its left. In the calculator I'm using, some of them you do it to the right, but the main thing is the thing immediately to the left gets squared. If that thing happens to be a parenthesis, then it's everything in the parentheses. So I can just type squared, even though I've got an 8 times 17 squared, it knows not to square the 8. 4 times 19 squared plus 2 times 25 squared plus 6 times 29 squared plus 34 squared plus 2 times 39 squared. And that gives me 14,492 meters squared per second squared, like that. And then all that will be divided by 25, and then the square root will be taken. Don't like my exponent there. Okay, so I'm going to divide this number by 25. And now I'm going to take the square root of that. And that gives me 24.07. And technically that should be 0.8. meters per second. So anybody have any questions with that? Okay, so that's the nuts and bolts of how you actually go about calculating these things, like root square, v squared bar, that kind of thing. Thanks, Richard. I see you got it fixed. All right, so let's take part C. Anybody have any idea what you're going to do to find part C? Or anybody know the answer right off the top of their head?
The velocity peak of the distribution.
Yeah, and that's what we did with the function, but this one's discrete. So we only have, we'd have like a bar chart basically. So that makes it a little bit problematic. But the trick here is to realize that most probable is the same thing as the one that occurs the most. Which one occurs the most here?
The 17 meters per second.
Exactly. So that's it. So V probable is equal to 17.0 meters per second, just because it turns out that in this collection of 25 particles, the speed that was represented most frequently was the speed of 17 meters per second, because that had 8 particles doing it, and the next highest only had 6. So, any questions on that? All right. So, let's try a van der Waals equation. So what I'm going to do, I think I might see if I can find one in the book to do a van der Waals problem. So I've done a couple of problems in here. Oh, actually, there's a couple problems I want to do anyways. So let's turn to here and let's say example. So example, by what factor will the RMS speed of gas molecules increase if the temperature is raised from, let's say, 0.0 degrees Celsius to 200.0 degrees Celsius. So that's a very nice problem. They're asking what factor, and this is a chance for you to see how symbolically working this out works much better and gives you more precise answers in some sense. You can't do much with this because this system requires you to use Kelvin temperature, and the Kelvin temperature is differentiated from the Celsius temperature via addition. So a lot of things don't cancel out like you'd like them to, so you can't just get a pure number. But anyways, they want to know what factor will the RMS speed be. So what we want is solution. What I'm looking for is VRMS at 200 divided by VRMS at 0. Again, this is 0 Celsius. So what we know is VRMS is equal to the square root of 3KT over M. Okay. So what we can do is we can say VRMS 200C over VRMS 0.0C is equal to, I'll just write one big square root. It'll be 3K. And this time we're going to write a temperature of 200 Celsius is 473.15 Kelvin divided by M, the mass of the molecules for the particular gas, and then 3K 273.15 Kelvin over the same molecular mass. So see, by doing it symbolically, we can see exactly that this 3 cancels out, which wasn't a big deal. We could have calculated that. This K cancels out. That wasn't a big deal either. But in this particular case, this M, we couldn't figure out at all unless we knew exactly what gas it was. So by doing it this way, using symbols, the variable that we thought we might need to know just fell right out, and we end up getting the square root of 473.15 Kelvin over 273.15 Kelvin. So when I do that, I say 473.15 divided by 273.15. That gives me the square root of 1.7322 roughly. No units there. And then I take the square root of that, and that gives me 1.316. So if you really do increase the temperature from 0 degrees Celsius to 200 degrees Celsius, you're only going to increase the velocity by a factor of basically 30%. So 1.30 times it, or 30% higher. Any questions on that? All right, so that's a pretty straightforward problem. A gas is at 30 degrees Celsius. To what temperature must it be raised to triple the root mean square speed? So there's another example. I should go ahead and box this. No one had any questions on this one, by the way? So a gas at, let's change it up a little bit. Let's say at 20.0 degrees Celsius is, whoa, is to have the RMS speed of its molecules tripled by how much must, whoa, Nelly, the temperature be raised. Okay. So I can treat this like I did before. I can say, for instance, solution. What we know is VRMS is equal to square root 3KT over M. What I want is VRMS2 over VRMS1 to be 3. Okay, so I can say VRMS2 over VRMS1 is equal to 3, and that's the square root. I'll actually just use one big square root like I did before. That's going to be 3K T2 over M divided by 3K T1 over M, which you can see ultimately just reduces to T2 over T1. And that tells you something to begin with. In order for the square root to be 3, then T2 equals 9. T1 implies VRMS2 over VRMS1 is equal to 3. So in Kelvin, I need the temperature to be 9 times as big. So I can say T2 is equal to 9.0. It's actually 9 to any number of decimal places times T1, and T1 was 273 plus 20. So this would be 293.15 Kelvin. So 293.15 times 9 gives me 2,638. And that's, quite a few extra sig figs, but anyways, that's the answer. Anybody have any questions on that one? Again, we're not doing much with temperature, boiling. We're not doing so much with vapor pressure and humidity as far as the homework goes. It is useful for you to know why a pressure cooker works. Temperature, boiling water, not messing with that. But let's just try this straightforward van der Waals equation problem. So your book gives a fairly straightforward van der Waals equation. It says in the van der Waals equation of state, the constant V represents the amount of unavailable volume per mole occupied by the molecules themselves. Thus, V is replaced by V minus NB, where N is the number of moles for oxygen. B is about 3.2 times 10 to the negative third cubic meters per mole. Estimate the diameter of an oxygen molecule. Oh, that's kind of a nice one. So this, I'll say, is problem number 41 of text. Okay, so y'all can read that for the actual description. What we say is van der Waals equation of state is P. I'm using lowercase again, so P minus NB times V is equal to nRT. And this is actually the Clausius version. We're not even taking into account the alter. Oh, no, we are actually. Sorry. I did it backwards. I'll just erase it. Makes it easier. So we're using basically V minus NB. All that would be times P, and that's equal to nRT. But with van der Waals, you'd alter some P as well. So this is just the Clausius one. And it's not really that relevant. But the main thing is this part right here is the same for the Clausius and the van der Waals. So I'll just leave that. It's not a big deal. The main thing is what we're told is B. Let's write it like this: solution. We're told that B for oxygen is equal to 3.2 times 10 to the negative fifth cubic meters per mole. And what they want to know is to estimate the diameter of the oxygen molecule. So oops. So what this tells us, dang it, not paying attention, I start thinking about the next thing and end up writing something goofy. Ah, dang it. That really went bad. Okay, so what this tells us is basically a mole of atoms takes up or a mole of molecules takes up 3.2 times 10 to the fifth cubic meters. So one atom or one molecule uses 3.2 times 10 to the negative fifth cubic meters per mole divided by Avogadro's number, like that. And that's going to give you cubic meters times, or actually cubic meters per atom or per molecule in this case. So we end up getting 3.2 times 10 to the negative fifth cubic meters per mole divided by 6.022 times 10 to the 23rd molecules per mole. And you see immediately that the mole cancels out with the mole, and the cubic meter on top and the molecules is left on the bottom. So we ultimately get cubic meters per molecule. And that answer will be 3.2 e to the negative fifth divided by 6.022 e to the 23rd gives me 5.313 times 10 to the negative 29th. And that's cubic meters. That's a 29 there. Cubic meters per mole, per molecule. Okay. So if we go on the assumption that a molecule is spherical, then the volume of a molecule is equal to 4/3 pi r cubed. So 4/3 pi r02 cubed is equal to 5.313 times 10 to the negative 29 cubic meters, gives us R of O2 is equal to. So now what I'm doing is I'm taking the 5.313 times 10 to the negative 29, I'm multiplying it by 3, and then I'm dividing it by parenthesis 4 times pi, and now I'm taking the cube root of that, and that was, once I multiplied by 3 and divided by 4 pi, I got 1.269 times 10 to the negative 29th cubic meters. Now I'm going to take the cube root of that, which is the same thing as the 1/3 power. So I raise it to 1/3 power, and I get RO2 is equal to 2.33, well, 332 times 10 to the negative 10th meters, which means the diameter of O2, remember it asked for diameter, so we got to multiply that by 2. So that's going to give me 4.7 times 10 to the negative 10th meters. So comparable again to the size of just a normal hydrogen atom, 10 to the negative 10th meters. Anybody have any questions on that one? All right, well, I think that's plenty. You can look up some other problems at the end of your chapter. What I tell students every semester, though I only find a couple that actually do it, is I tell students every semester that what they might want to do is sort of read over the chapter. Then when you get done reading the chapter, you might find that some of the areas didn't sit that well with you, didn't understand that well. So maybe you reread those sections. And also, by the way, you sort of need to slowly transition yourself to be able to read for a long period of time. Most people can't read something that's quote unquote boring. They can't read that but for a couple of minutes before they lose their attention span. So you got to train yourself to increase your attention span even for the most boring stuff. So when you're reading a book, try to see how long it takes when you're sitting there before you actually get bored, especially if you're reading something boring, and then use that as your time limit. So if it turns out to be 2.5 minutes, then you're only going to read for 2.5 minutes. And you read for 2.5 minutes, you stop, take a break, go do something, do some other kind of work, maybe solve a problem or something like that. Then go back, read again. After you've done that maybe about 5 or 10 times, you might try upping it by, let's say, 10%. So maybe instead of 2 minutes and 30, which was what, 150. So maybe you add 15 seconds, maybe you add 20. So you can maybe try 245 next or 250 next or something like that. Might even round up to the next minute. Once, if you find that that works for you, then do that 5 or 10 times and keep increasing. But once you get that down, then read the whole chapter, not necessarily in one setting unless you've worked up to be able to read it in one setting, and then read the synopsis at the end of the chapter, and that should give you an idea of anything you felt kind of shaky about. Maybe you go reread the sections you didn't understand that well. And then what I would do is I'd start looking at the low numbered in each subsection at the end of the chapter. I'd look at the low number odd problems. So for instance, I'm looking right now at this textbook and I'm looking in the problems. And what I see is once we get to the problems, that's problem 1, 2, 3. There's section 18.1. So I would possibly try 1, 3, and maybe 5 just to make sure I know what I'm doing. And then I look at section 18.2, which starts with number 20. And maybe I just do 21 and 23. And then I go to 18.3 if that was the section I cover, and maybe look for just one of the odd problems. Once you've done those odd problems, you know what the right answer is because it's in the back of the book, and you can see whether you're doing it right. Once you've done a few of those, then you're probably in a much better state to start your homework and your practice tests. So that's something you can always do. It's also something you can come back and do if you start your homework and you're not getting it. Okay, so if you're finding that you have to look up too much stuff on Chegg, which I want you to do because I would like you to get as good a grade as possible on homework, but I want you to do it responsibly, which means you got to learn, not just, see how it's done and then memorize it. So you don't want to do Chegg too early. Ideally, the best case scenario would be try to solve it. If you can't get it, open up Chegg, look at what they did, close Chegg, and then try to solve it again. If that doesn't work, try going back to the same subsection within the end of the chapter and look for an odd problem and try to solve that, especially one that's like it. A lot of times you'll find the actual problem that's in your homework as a text problem with slightly different numbers. And then sometimes you even see, oh, wow, in the book they gave me this hint, whereas they didn't give me that hint in the homeworks. So when I was hired to write these questions for Giancoli's textbook, not in the 5th edition, I did the 2nd and 3rd edition. That was largely what we were told to do. We just go in and grab homework problems and render them as algorithmic and put them in the homework system. We had to write them with some kind of pseudocode and stuff like that. But anyways, hopefully that'll help you. It's now 6:39. It's time for you guys to go. I'll wait for the last person to leave. Your homework is due Sunday, 11:59 p.m. You should have no problem doing that. Do keep an eye out on whether I open up the lab Canvas page, because that might be where you're going to. And I'd also like anybody that's taking my lab class during the day, please email me and let me know. I know Shanda's doing it, and I know Logan's doing it. I know Micah's doing it, but that's about it. So I need to request that you students be put in the Canvas course. So anybody else that's doing that, please let me know. Have a good one, everybody. I'll wait for the last person to leave in case anybody has any questions. Is it Shonda, by the way, Shanda, or is it Shanda?
It's Shonda. It's okay. I'll have to send you an email. My dad got diagnosed with cancer yesterday, so I'll talk to you later. But I'm getting the work done. Bye.
Okay, I'm sorry, Shonda. Have a good one. Wish the best for your dad.